Picture a galaxy so ancient its stars have been burning for 13 billion years, yet the universe itself was only 500 million years old when we saw it. The James Webb Space Telescope has uncovered such galaxies, their glow-revealing star-forming regions that seem to have been quietly churning for billions of years in a cosmos that was still a toddler. How is this possible? Because the light we see today left those galaxies when the universe was less than a billion years old, meaning the galaxies themselves are older than the universe was at the time of their observation. This isn't just a paradox, it's a revolution in our understanding of cosmic infancy. These galaxies, cradled in the darkness of the early universe, defied expectations by building vast stellar cities in a time when the cosmos should have been too young, too sparse, too chaotic to host such structures. What secrets are they hiding? And how did they manage to form stars so quickly, so completely, in a universe that hadn't even finished birthing its first stars? The universe is 13.8 billion years old. Webb is finding galaxies that look like they've been quietly forming stars for billions of years inside a cosmos that was, at the time of observation, only a few hundred million years old. This part of our deep dive into the universe is 13.8 billion years old. Webb is finding galaxies that look like they've been quietly forming stars for billions of years inside a cosmos that was, at the time of observation, only a few hundred million years old. Focuses on, explain plainly what was actually discovered/announced. Lead with the single most important fact, then fill in the necessary detail. A curious newcomer needs to understand it. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. The James Webb Space Telescope has rewritten our understanding of the early universe by peering back billions of years to observe galaxies that seem to have been quietly forming stars for eons. But how did scientists uncover this? The answer lies in a combination of cutting-edge technology, patient observation, and the unique properties of light itself. To grasp this, we need to start with the basics of how telescopes like Webb work. When we look at distant objects in space, we're not seeing them as they are right now, we're seeing them as they were when the light left them. Light travels at an incredible speed, but even at that speed, it takes time to cross the vast distances of the cosmos. So, when we observe a galaxy that appears to be only a few hundred million years old, we're actually looking at it as it existed when the universe was just a fraction of its current age. But how did Webb detect galaxies that seem to have been forming stars for billions of years in such a young universe? The key lies in the telescope's ability to capture light that has been stretched over unimaginable distances. The universe is 13.8 billion years old, but the light from these ancient galaxies has traveled for nearly that entire duration to reach us. By measuring how much the light has been stretched, known as redshift, scientists can calculate how far away these galaxies are and, consequently, how long ago their light was emitted. For example, a galaxy observed when the universe was just 500 million years old would have its light stretched into the infrared spectrum, a range of wavelengths that Webb is uniquely equipped to detect. This infrared capability is crucial because the light from these distant galaxies is shifted into longer wavelengths due to the expansion of the universe. Without instruments like Webb's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, such observations would be impossible. These instruments are designed to capture faint, distant signals with extreme precision, allowing scientists to detect galaxies that are otherwise invisible to older telescopes. But even with these advanced tools, the process of discovering these galaxies was far from straightforward. The challenge was twofold. First, the galaxies themselves are incredibly faint, and second, their light has been stretched so much that it appears in wavelengths that require specialized detection. To overcome this, scientists had to employ long exposure times, allowing the telescope to gather enough light to form clear images. Each observation required meticulous planning, as the telescope's mirror and instruments had to be calibrated to account for the faint signals and the vast distances involved. Once the data was collected, it wasn't just about capturing images, it was about interpreting them. The light from these galaxies contains a wealth of information. By analyzing the spectrum of the light, scientists can determine the composition of the galaxies, the age of their stars, and even the rate at which new stars are forming. For instance, the presence of certain elements in the light spectrum indicates the presence of older stars, while the brightness of specific wavelengths can reveal how actively stars are being born. This analysis is what led to the surprising conclusion: these galaxies appear to have been forming stars for billions of years, even though the universe was only a few 100 million years old at the time of observation. But how does that make sense? The answer lies in the timeline of the universe's evolution. The universe began with the Big Bang, a cosmic explosion that set the stage for the formation of stars and galaxies. In the first few 100 million years, the universe was a hot, dense plasma, and it took time for the first stars to form. These early stars, called population 3 stars, were massive and short-lived, but their light would have been the first to illuminate the cosmos. However, the galaxies observed by Webb are not just remnants of these early stars, they are entire systems of stars, gas, and dark matter that have been actively forming stars for a much longer period. This suggests that the process of galaxy formation began earlier than previously thought, or that these galaxies have a longer history of star formation than expected. The implications of this discovery are profound. It challenges existing models of how galaxies formed in the early universe. Previously, scientists believed that the first galaxies formed relatively quickly, perhaps within the first few 100 million years, but this new evidence suggests that some galaxies may have been forming stars over a more extended period. This could mean that the universe's early history was more complex and dynamic than previously imagined. The process of confirming these findings also involved cross-referencing data from other telescopes and observations. For example, the Hubble Space Telescope had previously detected some of these distant galaxies, but Webb's infrared capabilities allowed for a much more detailed analysis. By combining data from multiple sources, scientists could build a more accurate picture of these galaxies' properties and their place in the universe's timeline. Another critical aspect of this discovery is the role of dark matter. While dark matter itself cannot be directly observed, its gravitational influence plays a key role in the formation of galaxies. The presence of dark matter in these early galaxies would have provided the gravitational scaffolding necessary for stars and gas to clump together and form galaxies. Understanding the distribution of dark matter in these systems is an ongoing area of research, as it helps explain how galaxies could have formed so quickly. The journey to uncover these galaxies also highlights the importance of patience and perseverance in scientific discovery. Observing such distant objects requires not only advanced technology but also years of planning and data collection. The James Webb Space Telescope's mission is a testament to human ingenuity, as it represents decades of research, engineering, and collaboration to build an instrument capable of peering back to the universe's infancy. Every image captured by Webb is a snapshot of a time when the cosmos was still young, and each observation brings us closer to understanding the origins of galaxies and the stars that light our night sky. The process of interpreting these observations is equally complex. Scientists must account for the vast distances involved, the effects of cosmic expansion, and the limitations of their instruments. Even small errors in measurements can lead to significant misinterpretations, so the analysis is meticulous. For example, determining the exact redshift of a galaxy requires precise calibration of the telescope's instruments and careful analysis of the light spectrum. Once the redshift is measured, scientists can calculate the galaxy's distance and, consequently, how long ago its light was emitted. This information, combined with spectral analysis, allows them to estimate the galaxy's age and star formation history. The fact that these galaxies appear to have been forming stars for billions of years suggests that their star formation processes are more sustained than previously thought.
This could mean that the galaxies are not just remnants of the first stars but are actively evolving systems with complex histories.
The implications of this discovery extend beyond the study of individual galaxies.
It offers insights into the broader processes that shaped the universe's evolution. By understanding how galaxies formed and evolved in the early universe, scientists can better model the distribution of matter, the formation of large-scale structures, and the eventual emergence of the galaxies we see today. This knowledge is essential for refining our understanding of the universe's history and its future. The discovery also raises new questions. For instance, how did these galaxies manage to form stars so quickly? What role did dark matter play in their formation? And how do these early galaxies compare to the ones we see in the present-day universe?
These questions drive ongoing research and highlight the importance of continued exploration. The James Webb Space Telescope is not just a tool for observation, it is a gateway to understanding the universe's past. Each galaxy it observes is a piece of a larger puzzle, helping us piece together the story of how the cosmos evolved from a hot, dense state to the vast, complex structure we see today. The process of discovery is as much about the technology that enables observation as it is about the scientific ingenuity required to interpret the data. It is a reminder that the universe is full of mysteries waiting to be uncovered, and that with each new observation, we come closer to understanding our place in the cosmos. In the end, the journey to uncover these galaxies is a testament to human curiosity and the relentless pursuit of knowledge. It is a story of collaboration, innovation, and the enduring quest to explore the unknown. And as we continue to look deeper into the universe, we are reminded that the cosmos is still full of secrets waiting to be discovered. The universe is 13.8 billion years old. Webb is finding galaxies that look like they've been quietly forming stars for billions of years inside a cosmos that was, at the time of observation, only a few 100 million years old. This part of our deep dive into the universe is 13.8 billion years old. Webb is finding galaxies that look like they've been quietly forming stars for billions of years inside a cosmos that was, at the time of observation, only a few 100 million years old. Focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For centuries, humanity gazed at the night sky, wondering about the cosmos' origins. But it wasn't until the early 20th century that scientists began to unravel the universe's age and structure. The story starts with Edwin Hubble, an astronomer whose work in the 1920s and 1930s transformed our understanding of the cosmos. Before Hubble, the prevailing belief was that the universe was static, a fixed, unchanging expanse of stars and galaxies. But Hubble's observations of distant galaxies revealed something astonishing: these galaxies were moving away from us, their light stretched into the red end of the spectrum. This redshift, as it came to be known, suggested that the universe itself was expanding. If the universe was expanding, then it must have had a beginning, a moment when all matter and energy were compressed into an incredibly dense state. This idea, later called the Big Bang Theory, was a radical departure from earlier cosmological models, but it laid the foundation for understanding the universe's age. However, the Big Bang Theory wasn't immediately accepted.
Many scientists hesitated, as it challenged the long-held notion of a static universe.
It wasn't until the 1960s that evidence for the Big Bang became more concrete. In 1964, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation, a faint glow of light permeating the universe.
This radiation, a remnant of the Big Bang's intense heat, provided the first direct evidence that the universe had a beginning. The discovery confirmed that the universe was not just expanding but had a specific age, though the exact number remained uncertain. Over the following decades, scientists refined their calculations.
The key was measuring the universe's expansion rate, known as the Hubble constant. Early estimates varied widely, but as technology advanced, more precise measurements emerged. The Hubble Space Telescope, launched in 1990, played a pivotal role in this effort. By observing distant galaxies and their redshift, Hubble provided data that allowed astronomers to calculate the universe's age with greater accuracy.
However, even with Hubble's capabilities, there were limits.
The telescope's optical instruments could only detect light in the visible spectrum, meaning it couldn't peer far enough back in time to study the earliest moments of the universe. The universe's expansion also stretched the light from distant objects, shifting it into longer wavelengths into the infrared range. This meant that to observe the universe's infancy, astronomers needed a telescope with unprecedented sensitivity to infrared light. Enter the James Webb Space Telescope, launched in 2021. Webb's design, with its massive mirror and advanced instruments, allows it to detect light from galaxies that formed just hundreds of millions of years after the Big Bang. These galaxies, so distant that their light has taken billions of years to reach us, offer a glimpse into the universe's earliest epochs.
But how did we get to this point?
The journey to understand the universe's age and structure has been a gradual, incremental process.
In the mid-20th century, the Big Bang theory gained traction, but it was still unclear how old the universe truly was.
The 1970s and 1980s saw the development of more sophisticated models, incorporating factors like dark matter and dark energy. These mysterious components, which make up most of the universe's mass and energy, influence its expansion in ways that were only beginning to be understood. The 1990s brought the Hubble Space Telescope's launch, which revolutionized our ability to observe distant galaxies.
Hubble's images revealed that the universe was not only expanding but accelerating in its expansion, a finding that hinted at the existence of dark energy.
This acceleration, first detected in the 1990s, further complicated the timeline of the universe's evolution.
By the 2000s, the Planck satellite, launched by the European Space Agency, provided the most precise measurements of the cosmic microwave background.
Planck's data refined the universe's age to approximately 13.8 billion years, a figure that has since become widely accepted.
Yet, even with these advancements, there were still gaps in our understanding. For example, how did galaxies form so quickly after the Big Bang?
Earlier models suggested that galaxies formed in a relatively short period, but observations from Hubble and other telescopes hinted at a more complex process. The James Webb Space Telescope is now pushing these boundaries further. Its ability to detect faint, distant galaxies has revealed structures that challenge existing theories. These galaxies, observed when the universe was only a few 100 million years old, appear to have been quietly forming stars for billions of years. This finding is perplexing because it suggests that the universe's earliest galaxies may have formed in a more gradual, sustained manner than previously thought.
Such discoveries force scientists to reconsider the timeline of cosmic evolution. The implications are profound.
If galaxies were forming stars for such a long time in the early universe, it could mean that the processes of star formation and galaxy assembly are more continuous than previously believed.
This challenges the idea that galaxy formation occurred in rapid bursts and suggests a more nuanced, extended history. But how did we arrive at this point? The answer lies in the cumulative efforts of generations of scientists and engineers.
Each mission, from Hubble to Planck to Webb, built on the discoveries of the past. The development of infrared technology, the refinement of observational techniques, and the integration of theoretical models have all contributed to our current understanding.
The James Webb Space Telescope represents the culmination of decades of scientific progress, allowing us to peer deeper into the cosmos than ever before.
Yet, even with Webb's capabilities, there are still mysteries to solve.
The universe's age is well established, but the processes that shaped it remain an active area of research. The galaxies observed by Webb are not just distant objects, they are windows into the past, offering clues about the universe's earliest moments. As scientists continue to analyze Webb's data, they may uncover new insights that reshape our understanding of cosmic history. The journey to uncover the universe's secrets is far from over, but each step brings us closer to answering the questions that have fascinated humanity for millennia. The James Webb Space Telescope has revealed galaxies that seem to have been quietly forming stars for billions of years, even though the universe was only a few 100 million years old at the time of observation. This discovery challenges our understanding of how the cosmos evolved, raising profound questions about the timeline of star formation, the role of dark matter, and the fundamental processes that shaped the early universe. While the universe is 13.8 billion years old, a figure established by decades of observations and the cosmic microwave background, the existence of these ancient galaxies suggests that some processes may have unfolded far more rapidly than previously imagined. But how can galaxies form stars for billions of years when the universe itself was still in its infancy? And what does this mean for the theories that have guided our understanding of cosmic history? These are the questions that scientists are still grappling with, and they lie at the heart of one of the most exciting and unresolved debates in modern astrophysics. One of the first mysteries these findings present is the timeline of star formation. According to the standard model of cosmology, the universe began with the Big Bang, and in the first few 100 million years, the first stars and galaxies began to form. However, the observations from Webb suggest that some galaxies may have already been producing stars at a significant rate just a few 100 million years after the Big Bang. This seems to contradict the idea that galaxy formation is a slow, gradual process. If these galaxies were forming stars for billions of years in a universe that was only a few 100 million years old, it implies that the process of star formation may have been more efficient or accelerated than previously thought. But how could this have happened? Was there an abundance of gas available to fuel star formation, or did some unknown mechanism allow stars to form more rapidly? These questions remain unanswered, and they highlight a gap in our understanding of the early universe. Another key question revolves around the role of dark matter in the formation of these ancient galaxies. Dark matter, which makes up about 27% of the universe's total mass energy content, is thought to have played a crucial role in the formation of large-scale structures like galaxies. Its gravitational pull helped clump together ordinary matter, allowing galaxies to form. However, the presence of these early galaxies raises questions about how dark matter interacted with ordinary matter in the first few 100 million years. If galaxies formed so quickly, did dark matter behave differently in the early universe? Did it clump together in ways that allowed for the rapid formation of massive structures? Or did the distribution of dark matter itself change in ways that we have yet to account for? These possibilities suggest that our current models of dark matter may need to be refined, or that there are aspects of dark matter's behavior that remain unknown. The observations also challenge our understanding of the cosmic timeline, particularly the period known as the Epoch of Reionization. This was a critical phase in the universe's history when the first stars and galaxies began to emit ultraviolet light, ionizing the neutral hydrogen that filled the cosmos. The Standard Model predicts that this process took place over several 100 million years, as galaxies formed and their radiation gradually cleared the universe of neutral gas. However, the presence of galaxies that formed stars so early suggests that this ionization may have occurred much faster than previously thought. If these galaxies were already producing significant amounts of radiation, they could have contributed to reionizing the universe in a shorter timespan. This would mean that the timeline of cosmic history is more compressed than we believed, and it raises questions about how the interplay between galaxies and the intergalactic medium unfolded. Did the first galaxies form in such a way that they rapidly altered the environment of the cosmos? Or were there other factors at play that accelerated this process? The implications of these findings also extend to our understanding of star formation itself. The Standard Model of star formation suggests that the first stars, known as population 3 stars, formed from primordial gas composed almost entirely of hydrogen and helium. These stars were massive and short-lived, but they played a crucial role in seeding the universe with heavier elements. However, the presence of galaxies that formed stars for billions of years in the early universe suggests that the process of star formation may have been more complex or efficient than previously thought. Did these galaxies contain a mix of population 3 and population 2 stars, or did they form stars in a way that defied the standard models? If so, what does that mean for the chemical evolution of the universe? These questions point to the possibility that our understanding of star formation is incomplete, and that the early universe may have harbored processes that are still not fully understood. Another layer of complexity arises from the observational techniques used to detect these ancient galaxies. The James Webb Space Telescope's ability to peer into the early universe is due to its sensitivity to infrared light, which allows it to observe objects that are so far away their light has been stretched into the infrared spectrum. However, the detection of these galaxies relies on their brightness and the way their light has been redshifted over cosmic distances. This means that the galaxies we observe are not necessarily representative of all early galaxies, but rather those that are particularly luminous or have unique properties that make them stand out. This raises the question of whether these galaxies are exceptions or if they represent a broader trend that we have yet to fully appreciate. If the galaxies we see are outliers, then our understanding of the early universe may be skewed. But if they are part of a larger pattern, then our models of galaxy formation may need to be revised to account for a more rapid or widespread process of star formation. The debate over these findings also touches on the broader question of how the universe evolved from its earliest moments to its current state. The standard model of cosmology, known as the lambda-CDM model, has been remarkably successful in explaining the universe's large-scale structure, the distribution of galaxies, and the cosmic microwave background. However, the existence of these ancient galaxies suggests that there may be aspects of this model that are incomplete or that require modification. For example, if galaxies formed so quickly, did the universe's expansion rate differ from what we currently believe? Or did the initial density fluctuations that seeded galaxy formation occur in a way that we have not yet accounted for? These possibilities highlight the fact that while the lambda-CDM model is our best current framework, it is not infallible, and there may be unknown factors that influence the universe's evolution. Perhaps the most intriguing aspect of these findings is the way they challenge our assumptions about the universe's timeline. The universe is 13.8 billion years old. But the presence of galaxies that formed stars for billions of years in its infancy suggests that some processes may have occurred far more rapidly than expected. This raises the question of whether the universe's history is more compressed than we thought, or if there are mechanisms at play that allow for such rapid development. For example, could the formation of these galaxies have been driven by factors we have not yet considered, such as the presence of dark energy or the influence of quantum fluctuations in the early universe? These possibilities open up new avenues of research, but they also underscore the fact that our understanding of the universe is still evolving. The discoveries made by the James Webb Space Telescope are not just about what we have observed, they are about what we have yet to understand. In the end, the findings from the James Webb Space Telescope represent a profound shift in our understanding of the early universe. They challenge existing models, raise new questions, and suggest that the cosmos may have evolved in ways we have yet to fully grasp. The fact that galaxies appear to have been forming stars for billions of years when the universe was still young is not just a puzzle, it is a call to action for scientists to refine their theories, test new hypotheses, and explore the unknown. As we continue to gather data and refine our models, one thing is clear: the universe is still full of mysteries, and the journey to uncover them is just beginning. As we stand at the edge of a revolution in our understanding of the cosmos, the discoveries made by the James Webb Space Telescope have already begun to reshape our view of the universe's early history. But these findings are just the beginning. The next few decades will see a cascade of new missions, instruments, and observations that could either solidify, refine, or even challenge the picture we're beginning to piece together. These efforts will not only build on the groundbreaking work of JWST but also push the boundaries of what we think is possible in the study of the universe's infancy. Let's explore what's coming next and how it might change everything. One of the most anticipated follow-up missions is the Nancy Grace Roman Space Telescope, set to launch in the late 2020s. Named after the NASA astronomer who championed the idea of wide-field surveys, this telescope will carry a powerful camera capable of capturing vast swaths of the sky in a single shot. Its primary mission is to study dark energy and dark matter, but its capabilities will also allow it to peer into the early universe with unprecedented precision.
By mapping the distribution of galaxies across cosmic time, the Roman telescope could help us determine whether the galaxies JWST has observed are truly rare anomalies or part of a broader trend. Its ability to detect subtle variations in light from distant objects will also enable scientists to study the chemical composition of these early galaxies, offering clues about how they formed and evolved. If the Roman telescope confirms that star formation began earlier and more vigorously than previously thought, it could force astronomers to reconsider the timeline of cosmic evolution.
Another key player in this next phase of exploration is the Euclid mission, a space observatory developed by the European Space Agency, ESA, and set to launch in 2023. Euclid's primary goal is to investigate the nature of dark energy, the mysterious force driving the universe's accelerated expansion. However, its advanced instruments, particularly its high-resolution camera and spectrograph, will also allow it to study the distribution of galaxies in the early universe. By analyzing how light from distant galaxies is bent by the gravitational pull of dark matter, Euclid could provide critical insights into the role of dark matter in shaping the cosmic web. If these early galaxies are found to be clustered in ways that suggest a dense network of dark matter, it would support the idea that the universe's structure was already beginning to take shape in the first few 100 million years. Conversely, if the data reveals unexpected patterns, it could hint at new physics beyond our current understanding of gravity and matter. On the ground, the extremely large telescope, ELT, currently under construction in the Atacama Desert of Chile, promises to revolutionize our ability to study the early universe. With a primary mirror 39 meters in diameter, nearly twice the size of the largest existing telescopes, the ELT will be capable of capturing light from objects that are billions of light-years away with unprecedented clarity. Its adaptive optics system will allow it to compensate for the blurring effects of Earth's atmosphere, making it possible to observe distant galaxies in exquisite detail. The ELT's instruments, including the high-resolution spectrograph and the Mikado imager, will enable astronomers to measure the chemical signatures of stars in these ancient galaxies, revealing whether they contain heavier elements or if they formed from primordial gas. Such data could help determine whether the star-forming processes observed by JWST are indicative of a universal trend or an exceptional phenomenon. If the ELT finds evidence of widespread early star formation, it would suggest that the universe's cosmic recipe was already in motion much earlier than previously believed. Beyond these large-scale missions, smaller but highly specialized instruments are also set to play a crucial role. The SphereX mission, a NASA-funded satellite scheduled for launch in the mid-2020s, will conduct a comprehensive survey of the sky in ultraviolet and visible light. Its primary objective is to map the distribution of galaxies and their star-forming activity across cosmic time, but its data could also provide critical context for JWST's findings. By measuring the light from millions of galaxies, SphereX will help astronomers identify patterns in star formation rates and determine whether the galaxies observed by JWST are part of a broader trend or an isolated case. Additionally, the mission's ability to detect subtle variations in the light from distant objects could help scientists distinguish between different types of star-forming regions, shedding light on the mechanisms driving early cosmic evolution. Another exciting development is the potential for new technologies to enhance our observational capabilities. For example, the upcoming LUVOIR, Large Ultraviolet Optical Infrared Surveyor, and the Habitable Worlds Observatory are two proposed space telescopes that could significantly expand our ability to study the early universe. LUVOIR, if approved, would feature a mirror up to 15 meters in diameter, allowing it to capture light from the faintest and most distant objects. Its advanced spectrographs would enable scientists to analyze the chemical composition of early galaxies with greater precision, potentially revealing whether they contain the same elements as galaxies formed later in cosmic history. The Habitable Worlds Observatory, while primarily focused on exoplanets, would also have the capability to study the light from distant galaxies, providing complementary data to missions like JWST and Roman. These next-generation instruments could help resolve long-standing questions about the universality of star formation processes and the role of environmental factors in shaping galaxies. However, the future of this field is not without challenges. One of the most pressing questions is whether the galaxies observed by JWST are truly representative of the early universe or if they are outliers that require a revision of our models. If future missions fail to confirm the widespread nature of early star formation, it could indicate that our current understanding of galaxy formation is incomplete.
For instance, if the data suggests that these galaxies formed under unique conditions that are not replicated elsewhere, it might imply that the universe's early history was more chaotic and varied than previously thought. Such findings could necessitate a re-evaluation of the standard cosmological model, which assumes a relatively uniform and predictable evolution of the universe.
Another area of uncertainty lies in the role of dark matter and dark energy in shaping the early universe.
While JWST's observations have provided tantalizing hints about the presence of massive galaxies in the first few 100 million years, the mechanisms that allowed them to form so quickly remain unclear. Future missions like Euclid and the Roman telescope could help clarify this by providing more detailed maps of the cosmic web and the distribution of dark matter. If these missions reveal that dark matter played a more active role in galaxy formation than previously assumed, it could lead to a paradigm shift in our understanding of how structure emerged in the universe. Conversely, if the data suggests that dark matter's influence was less significant, it might point to alternative theories about the nature of gravity or the composition of the universe.
In addition to confirming or challenging existing theories, future observations could also open up entirely new avenues of research.
For example, the study of early galaxies might lead to insights into the nature of the first stars, known as population 3 stars. These hypothetical stars, composed almost entirely of hydrogen and helium, are thought to have formed in the first few 100 million years after the Big Bang. However, their existence has never been directly observed, and their properties remain a subject of debate. If future missions can detect the faint signatures of these stars or their remnants, it would provide critical evidence about the early stages of stellar evolution and the conditions of the universe's infancy. Such discoveries could also help us understand how the first galaxies assembled and how they contributed to the formation of the cosmic web.
Moreover, the study of early galaxies could have implications beyond cosmology, touching on fields such as astrophysics and even planetary science. For instance, understanding the chemical enrichment of the early universe could shed light on the processes that led to the formation of the elements necessary for life. If the data suggests that heavy elements were produced more rapidly than previously thought, it could challenge existing models of stellar nucleosynthesis and the timeline of element formation. These insights might also inform our understanding of how life emerged in the universe, potentially offering clues about the conditions required for the development of complex structures. As these missions and instruments come online, the scientific community will face the challenge of interpreting the data they produce. The sheer volume of information generated by these observatories will require advanced computational tools and collaborative efforts across disciplines. Machine learning algorithms, for example, could help astronomers sift through vast datasets to identify patterns and anomalies that might otherwise go unnoticed. International collaborations will also be essential, as the scale of these projects often exceeds the resources of any single institution. By pooling expertise and data, scientists can ensure that the findings from these missions are rigorously analyzed and integrated into a cohesive picture of the universe's history. In the end, the next few decades will be a period of intense discovery and transformation in our understanding of the cosmos. The findings from JWST have already forced us to reconsider the timeline of galaxy formation, but the future holds the promise of even more profound revelations. Whether these missions confirm our current theories, challenge them, or reveal entirely new phenomena, they will undoubtedly deepen our appreciation of the universe's complexity and beauty. As we continue to look further back in time, we are not just uncovering the secrets of the past, we are also gaining a clearer picture of the forces that have shaped the universe we see today. And in doing so, we are laying the foundation for the next great leap in our quest to understand the cosmos. The universe is 13.8 billion years old.
Webb is finding galaxies that look like they've been quietly forming stars for billions of years inside a cosmos that was, at the time of observation, only a few 100 million years old. This part of our deep dive into the universe is 13.8 billion years old. Webb is finding galaxies that look like they've been quietly forming stars for billions of years inside a cosmos that was, at the time of observation, only a few 100 million years old. Focuses on, briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.